Okay guys, let's start with the revision for the math periodic. Hope you guys are doing well, and we'll start with the section 4.2.1. So this section deals with implicit differentiation. Traditionally normal derivatives we do is with one variable, x, y, z, whatever, but it's with one. But sometimes we're given functions like this with two variables. So then our normal definitions don't work, and that's why we use implicit differentiation, where we treat one variable. In this instance we always treat y as the function. So let's just solve activity 2 number 1. Why I'm not solving activity 1 or activity 2 number 3 is because activity 1, the answer, the way you solve it is given in activity 2 number 1. We will do it, and activity 2 number 3, there's a grid question similar to that. So let's start without any further ado, and I'll give you guys a few seconds to solve. Okay, let's check it together. Given 2xy plus y squared equals x plus 1, find basically y double prime. So basically activity 1 needs us to find y prime of this. So we are doing activity 1 in this question as well. So to find y prime, it's basically you use the product rule kind of thing here. It's two variables, so it's 2y plus 2xy prime plus 2y prime equals 1. Take the y prime out, you get 2x plus 2y equals 1 minus 2y. So y prime is equal to 1 minus 2y over 2x plus 2y. And this is actually the answer for activity 1. So yeah. Now y prime is equal to 1 minus 2y over 2x plus 2y. We want y double prime, so we use the quotient rule. So we get minus 2y prime into 2x plus 2y minus 2 plus 2y prime into 1 minus 2y all over, let's take the 2 out for now, x plus y squared. Now basically, since we have y, y prime, so we have to substitute 1 minus 2y over 2x plus 2y into 2x plus 2y, 2 plus you just substitute 1 minus 2y over 2x plus 2y, parenthesis 1 minus 2y over 2x plus y squared. Now you have to go through the hassle of common denominator, simplifying. I'm not going to go into all that. It's simple algebra, and the final answer of y double prime that you should get is, now don't worry if you get a very long answer and it's nothing similar to this. You may have just gotten the expanded form. I've simplified it. 4x plus 2y plus 1, all of that over 4x plus y cubed. So this is the way how you solve it. Okay guys, let's start section 4.4.1. This section deals with linearizations. We use the linear model of a function to obtain estimates. As we can see, obtain an estimate for given values. And this section deals with getting the equation of the tangent line and finding estimates for certain values. So let's start with example 1, as this is on the revision sheet for the periodic. Find the linearization of f of x equals square root of x at x equals 4. Use the linear model of f to obtain an estimate for these values. Compare the estimates with the answers the calculator gives and comment on the results. So I would give you guys a few seconds to solve, and let me just help you guys out. Split this question into 3 parts. Now when I've split it with these lines, now it gives you certain steps to work towards. I'll give you guys a few seconds. Okay, let's check it together. First, we find the linearization of f of x root x at x equals 4. Let's look at the point first. Since it's 4, we take the square root of 4, it's 2. So this is the point we're looking for the tangent at. What is the derivative? When you have to find the tangent, you have to find the slope. F prime of x is 1 over 2 radical x. Substituting at x equals 4, we get 1 over 4. So this is m, which is the slope of the tangent. Now we use y minus y0 equals mt. Remember, x minus x0. So if we substitute, we get y minus, we take this value, 2 equals 1 over 4 x minus 4. When we finally solve, we get y equals 1 over 4x minus 1 plus 1. But this is not the linearization, right? We're looking at the linearization. If they wanted the tangent, this is the tangent. One simple step, L of x is equal to 1/4 x plus 1. And this is the linearization of f of x equals square root of x at x equals 4. Now we move on to the second part of the question. Use the linear model of f to obtain an estimate for square root of 4.1, square root of 5 and square root of 6. So moving on, let's just have the quick equation here. And let's just remember what f of x is. They wanted square root of 4.1. Well, let's look at square root of 4.1. Isn't this f of 4.1? Because if we put 4.1 in x, then f of 4.1 is square root of 4.1, right? And we should know that the definition itself says this is approximately equal to. Linearization will never give us an exact value unless we're looking at the exact point, which is 4. So this is approximately L of 4.1, right? Which is approximately equal to, if we substitute 1 over 4 into 4.1 plus 1, which is again approximately, let's quickly check, 2.025. Same thing with radical 5 is equal to f of 5 approximately L of 5, which is again substituting, we get 5 divided by 4 plus 1, 2.25. And square root of 6 is f of 6, which is L of 6, 2.5. We have answered the second part. Compare the estimates with the answers a calculator gives and comment on the results. Basically, they want the exact values. Now we have square root of 4.1. Let me get the exact value. All I have to do is plug in your calculator. And we get 2.0248. I'm not going to write more digits. It doesn't make more sense. Square root of 5. Let's take the exact value. Is around 2.236, and the square root of 6, I'm just gonna draw a line here, calc. So we know that these are our exact values, and the square root of 6 is equal to 2.449. Let's put a 5 here. Okay, what do we see here? Well, we see, and this is answering the second part because we've compared it with the estimates. Comment on the results. We see that the values that we're getting with the linear model are extremely close. 2.025, 2.0248, they're rounding errors. But one thing to notice here, the closer we get to 4 or any point that was given in the question, not got to 4, get to 4, the more accurate the answer. What does this mean? Let's see. What is the difference from 2.0248 and 2.025? It's 0. Let's just quickly be correct. 2.025 minus 2.0248. 0.0002. The difference between this and this, 2.25 minus 2.236, would be a bit bigger, 0.014. And let's check the last one, 2.5 minus 2.4495. It's 0.0505. So as you can see, the differences are getting larger. So that shows that the closer we are to 4, which is the main point where we're taking the tangent, the more accurate our answers get. One more thing you can look at is, are your estimates underestimates or overestimates? Are you getting more than the real answer or less? In this case, our answers are overestimates. And one way to show this graphically is, I will be showing it to you right now. How does square root of x really look like? Just draw a quick graph. Doesn't it look like this? It's concaving down. Important thing. When you draw the tangent, it looks like this. So when you can clearly see, let me draw this with red. This is, let's say, 4. You can very clearly see that any of our answers will be over. Let's say this is 6. This is more than the real value. The real value is actually this. So that's why whenever the curve is concaving down, our linear model will always give us overestimates, and if it's concaving up like this, it will give us underestimates. And with this in our minds, let's solve the activity. I'll give you guys a few seconds and then we'll check together. Okay, let's check together. First, we have to find the linear model. So we derive this f prime of x, but first obviously we have to find the point. So it's at 0 comma 0 plus 0 1. F prime of x is x squared plus 1 to the minus half. Chain rule, it's minus half x squared plus 1 minus 3 over 2 times 2x. Well, this gives us minus 2x over 2 x squared plus 1 cubed. Cancel, and this is our derivative at x equals 0. Now you can see this is 0, so our slope is 0. Our slope is 0 because if you substitute anything, 0 over anything is 0. Now we get y minus 1 equals 0 into x minus 0, which leads to y equals 1, or L of x equals 1, and this is our linear model. Obtain an estimate for 1 over the square root of 1.04. We cannot immediately put this into the answer, even though anything we put will get 1, because the tangent is a horizontal line, but we have to use the right x. So we say 1 over square root of 1.04 equals 1 over the square root of x squared plus 1. 1 is the same, but now we have to split this. Can't we write this as 0.04? Oh wait, yeah, 0.04 plus 1. If we're just splitting it, we can write that, right? Now what squared? X squared equals 0.04. Then what does x equal? X is equal to plus or minus 0.2. Substituting here, f of 0.2 is approximately equal to L of 0.2, which is approximately equal to 1. And this is your answer. Let's do some grid questions related to this, shall we? Okay guys, let's move on to section 4.5, which is the next section required for the periodic. This section deals with solving equations graphically, solving them by rearranging, and what better way to learn than by solving this quick activity. So let's do activity 2 number 1. Show that the equation x minus e to the minus x equals 0 has a root between 0.4 and 0.6. Use the iterative formula xn plus 1 equals the square root of xn e to the minus xn with x0 given to be 0.6 to find the root to one decimal place. Okay, I'll give you guys a few seconds. You can solve and then we'll check together. Okay, let's check together. First step, to make it very simple for us, let's just quickly call this f of x. So f of x equals x minus e to the minus x equals 0. No, it's not equal to 0. It's just this. Now, next step, we have 0.4 and 0.6. I'm going to solve it and then I'll give you guys a few seconds to remember something. So let's see. F of 0.4, I've solved it beforehand. It is a negative value. You guys can find the exact value for yourselves, and you can even write it and then say this is negative, but you can easily write negative. And f of 0.6 is positive. Seeing this, what do you guys remember? We learned a theorem on this. Intermediate value theorem, IVT. So what we should say is, as f of x is continuous on the closed interval 0.4 and 0.6, it is definitely continuous because we know x is continuous and we know e to the minus x is continuous. if f of x and g of x are continuous, f minus g of x is also continuous, and f of 0.4 comma f of 0.6 have opposite signs, that means one is positive, one is negative, opposite signs, then we have fulfilled all the conditions of the intermediate value theorem. So then by IVT, f of x has a root between 0.4 and 0.6, and that this is the wording I should use in the written part, just to give the reasoning why why you did this step basically. Now that we have this, now we look at the iterative formula. We had xn plus 1 equals square root of xn e to the minus xn, and we also had given that x0 is 0.6 and they want the root to one decimal place. Now what we're supposed to do is you're just supposed to keep on substituting the values in this equation, just press equals and recording the values, and the moment you get two answers that round to the same number in one decimal place, that's your root. So we have x0 equals 0.6. I believe you guys can easily substitute. All you have to do is 0.6 times e to the minus 0.6 and square root that, and you just keep substituting. So in this case it would be smart to take it to maximum 3 decimal places, because maximum it will affect that. So as we can see here, the rounded value is 0.6 approximately, but it's better to be 100% sure. The next value you get is 0.569, and maximum x3 you should take is 0.567. In all of these cases it's rounding to 0.6, so what we say is the root is 0.6 to one decimal place, and that's how you solve activity 2 number 1. Let's do number 2 now. Using the same set of axes, sketch the graphs of y equals e to the x and y equals 1 over x. Okay, I'll give you guys a few seconds, you can solve and then we'll check together. Okay, let's check it now. See, you guys don't need to, if you want, you can do all the, derivatives and, y-intercept, x-intercept, it's good, but, it's a written exam, you want quick. But don't do a rough sketch, they want it as a question. So, it would be good, let's call f of x equals e of x and g of x is equal to 1 over x. Just take a few points. I hope you guys know how to solve it, graph it, and then when we graph we get x and y. You guys should know that e to the power of 0 is 1. It's a very important point. So e of x tends to look like this. Call it f of x, and you guys should know that 1 over x, to get a 1 over x, all you have to do is take a few points, right? And then that gives you the general shape. It is asymptotic to both axes and it looks somewhat like this. It's a very rough sketch I've done because I cannot do a proper sketch in this app, and that is how you're supposed to guess the graphs, and this is the point of intersection. Important point. B. Deduce the number of real solutions of this equation e of x equals 1 over x and show that this equation may be written in the form x minus e to the minus x equals 0. Well, now if you can see, there's only one point where they're intersecting, and then we call this is a point. So it has one real solution. And now let's see how we can rearrange this equation. We see that e of x equals 1 over x. Now we take, let's take the reciprocal, let's flip them. So that's x equals 1 over e to the x, right? When we solve this part, we should get x equals e to the minus x, because it's minus power. And then we just take this to the other side, we get x minus e to the minus x equals 0. And wait a second, this is looking extremely familiar. It's the same one from activity 1. But we shouldn't say that it's the same question. It's a different question, so let's resolve it. Now this time we have to show that it has a root between 0.5 and 0.6. So okay, let's call this new equation h of x is equal to x minus e to the minus x, and let's see, h of 0.5 and we take h of 0.6, and what do we get? H of 0.5 is equal to minus 0.107, which is negative, and h of 0.6 is 0.051, which is positive. Then we do the exact same thing, intermediate value theorem. If you guys want the wording, you can rewind a few seconds and see what I said in number 1. Blah 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 dot dot dot, we have a root. Let's move on to part D now. Taking x equals 0.6 as the first approximation to this root, let us use an iterative equation to find the root and giving our answer to one decimal place. Okay. Now we have as a given, and we can easily use that. We can just say x is equal to e to the minus x. All I've done is taken e to the other side, and then I can easily say x n plus 1 is equal to e minus x n. And we had x0 to be given as, what was it given as? 0.6. And they want it as one decimal place. We just keep approximating. We get 0.5488 dot dot dot. And for x2 we get 0.5776358 dot dot dot. And x3 we get 0.5612236194. This is all the numbers that are showing in my calculator. As we can see, 0.57 and 0.56 are extremely close values. Why I did not stop at 0.57 is because these two values round to different numbers, right? They want one decimal place, and since they both round to 0.6, our root is again 0.6 to one decimal place. And this is the final answer for part D. So now that we have done all the applications from the book, let's do a...
This one's really easy. It kind of like you could say self-explanatory. They're just testing you if you know how to split the summation, if you know how to split the constants from the variables when you do the summation. So pretty much, let's cut into the chase. Let's just split them. You end up with m cubed from 1 to 25 plus 2 outside into the summation of m from 1 till 25 plus 1 summation of 1 from m1 till 25. And this translates to that, this translates to that, and this translates to that. So just immediately write the rules. In here it will be 25 because your n is going to be the one above always. And so 25 times 26 squared over 4 plus 2 into, do not forget that there's a 2 outside, and then you have a fraction over here. It's 25 times 26 over 2, these cancel, and you have plus 25 over here because you just end up with n, and then you end up with the answer of 106,300. Fairly easy, to be honest. Okay. So for this exercise, we're going to use the summation rule to find the estimation of the area, not equal or exact value, because we're given a certain number of intervals. So even if you're using summation with the limit, it can give you the exact value. In here, it's just a certain number of intervals, so no limits. So I just did the integration just to show you that you're going to get a value similar to this. Something within that range, not like, for example, minus 77 or let's say plus 108. These are really far values, so just for you to see. Even if you get 15, pretty far. This is like 1.33. So yeah, let's keep on going. The very first step to do is find delta x. So b minus a over n. B is 1, A is 0, and n is 4. So 1 minus 0 over 4 gives you 1 over 4, length of the interval. And immediately your second step is to find the intervals themselves. You start with 0, so 0, plus 1 over 4, and then repeat 1 over 4, plus 1 over 4, you get half, and then again you repeat, add 1 over 4, you get 3 over 4. Again you repeat, add 1 over 4, you get finally 1. So we're going from 0 to 1 over the course of how many? 4 intervals, which is exactly what we want. So we know we're correct. We want ck. Ck is given here by right endpoint. So this is right endpoint, right endpoint, right endpoint, right endpoint. So these are our ck's basically. So when you do the summation, we need those ck's. But to be exact, we actually need the f of ck, which is some of the mistakes I used to do back then, which I don't want you guys to do. Which is, don't immediately use, even if you end up, let's say, writing it in the formula, which is what I used to do back then, I still end up, when I hold the calculator, I still end up putting this times that plus this times that, which is wrong. You need to put this in here, find f of ck, and then just multiply it there. So I already found the values, so I'll just be giving them to you guys, just save time. To be 9 over 16 for this one, 5 over 4, and this is 33 over 16, and this is 3. These values you've gotten from putting 1 over 4 here, putting half here, 3 over 4, 1, and so on. So the rule says summation of, and we're going to use ck, so I'm going to say k. If they use I, I'm going to use I. So k is 1, we want 4 intervals, so this is 4, times, or summation of delta x times f of ck. By the way, delta x is a constant, they're equal intervals, so just you can take it out, save time, especially on a calculator, because on a calculator you can just, if the delta x is outside, you're just going to be multiplying by a number, like something, times, and when the calculator you put plus, 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 whatever expression you have over there. So with that, delta x summation from 1 till 4 of f of x, ck and then from there delta x is what? 1 over 4 into, I said each one of those, I gave them the values, so 9 over 16 plus, this is 16, plus 5 over 4, plus 33 over 16, and finally plus 3. If you add them, you end up getting and multiplying. If you add them, actually you get 55 over 8. If you multiply by over 4, you get 55 over 32, which is approximately 1.71. Actually, exactly, if you calculate it, exactly 171.875, I think, which is roughly close to 1.333. So we know we're good, and this is pretty much how to get the value. So for this exercise, we're not given a certain number of intervals, so you just have to use Riemann's sum with n intervals, which is exactly this. And I'll be giving you tips on the way, so I prefer if you see this from beginning to end. So our very first step is to find delta x. Delta x is b minus a over n. N stays n, b is 3, a is 1, so 3 minus 1 over n, giving you 2 over n. The easiest way to find ck, which is what you need to find next, is to use the intervals. So you're starting from 1, so 1 plus, again this is not obligatory, it's just to find ck, an easy way to find ck. 1 plus, add 2n, so 2, you start with, of course, a, and then 1 plus 2 over n, and then again 1 plus 2 over n, comma 1 plus 2 over n plus 2 over n, so 1 plus 4 over n, and then add 1 last time. You get 6 over n for that part, for the small with the over n part, and then you just continue if you want, but you should stop really here, not to waste too much time. And so this helps you find ck. Ck is 1 stays constant, so write the constants. N is again a constant, nothing changing here. 2 became 4, became 6, you're doubling, and your actual only changing factor, which is k, goes from 1 to 2 to 3 to 4, so the only way you should have this is 2 times k. And we don't need our ck directly, we need f of ck, which is really important. F of ck, just put ck right over here into this equation. So you get 1 plus 2 into k over n squared plus 4 into 1 plus 2k over n. 1 squared, again 1, plus 2k over n times 1 times 2, you get 4k over n. If you're confused, all I did is a plus b squared. The middle value is 2ab, pretty much, that's it, 2ab. Plus the squared, so you have 4k squared over n squared, plus 4 into this, so you get 4 for this small part, and for this one, 4 times 2, you get 8k over n. And let's simplify further. If you don't mind, first of all, these are like terms, and if you don't mind, I'm gonna start with this, you know, like as in descending order of power. So 4k squared over n squared, because it looks nicer, plus 12k over n plus 5. So we have our f of ck, we have our delta x, we're ready to go with Riemann's sum. But one more note before we start, which is really important. This is Riemann's sum, and not this, which is really important. Like this, okay, yeah, Riemann's sum, but not this. There's a huge difference, because with the limit, it makes a huge difference. Because if you were to do this, let's say, write it on the exam, if you do, let's say you do write this, okay, but then if you end up solving and you don't have a limit, and then your limit pops up out of nowhere, or even without a limit, like you just progress like this, and you end up saying that just somehow substitute by dividing by the coefficients, because we know either way in the end we're going to divide by the coefficients, and you're going to end up with certain numbers, you're going to add them up and you get this, right? Well, this is due to the limit, so you need to write the limit. But the problem is, if you write the limit from the beginning, it's like a curse. If you start from the beginning, you have to keep on going. But to avoid this, one way I think of it, I think this is pretty much normal to do. One way to avoid this problem of writing the limit in the beginning and continuing, because you have to do limit, and then write, then equals limit, then write. If you forget one limit, I guess, I mean, they might not be as strict, but still, if you do write one limit, continue. But for this one, I'm gonna do this one trick, where I'm not gonna write the limit at the beginning, because I'm equating something to something. I'm not saying Riemann's sum is, no. I'm just immediately going with summation k equals 1 n delta x f of ck. Immediately I'm just saying this value. I'm segmenting the equation. This value is, and then I can continue with the other one. So this is, to save time, I'm going to try doing this quickly. Summation of from k1 till n, and then delta x is 2 over n, into this, which is 4k squared over n squared, plus 12k. You know how to simplify from here, but I'm just gonna do this with you guys. I'm gonna try going quickly, not to waste anyone's time. Here, this is 1 and n, and then this times that, you get 8k. I'll immediately take it out. Actually, no. Actually, let's just 8k squared over n cubic, plus this times that, that's 24k. Yeah, 24k over n squared, plus this times that, that's 10 over n. And then if you split this, the summations, you end up with k equals 1, here it's n, of 8 outside, n over n cubed outside, you're left with k squared. And then you know your rules with k and all that. So summation of k from 1 till n of k plus 10 over n, summation of 1 from 1 till n. For this one, you'll just end up with 8 into n cubic, or over n cubic, into with the square, you end up doing 2n plus 1 into n plus 1 into n over 6. You can cancel 2 here, 2 here. I'm doing this step because I know for sure that I do not care about the 1. I do not care about the 1 here, and do not care about anything else. I only care about what the n powers, because I want the highest power possible, and then from there compare it to this one. So if you multiply the n's, you get n cubic, which is the same power as n cubic over here. So you're gonna do the coefficients of those. The coefficients of n are only visible here and here. So 16 as opposed to 6 over here. This is why I wanted to cancel by 2 here and there. If you cancel by 2 before multiplying, you end up with 3 here, and this cancels. So 8 over 3, immediately the answer is 8 over 3 here for the coefficients, plus 24 over n squared into k. It gives you n into n plus 1 over 2. This cancels that, 12, and then you get n squared, and the coefficient is 12. 12 over 1, you get 12. The answer for this one's 12, plus 10 over n, then you get here n, immediately cancels. You get 10, 12, 8 over 3. Add them up, you get 74 over 3. And did we or did we not get the same exact value as the value over here? We got the same exact value, right? So we know that we're right. And with that we're pretty much done. So in this exercise we're gonna look for the area again, but this time using again definition, which is what we used earlier. Normally, like, you know, the limit of the summation of f ck times delta x, same thing. It's just that they also want the area of the trapezoid, which is this right over here, which is, you know, half base. In here, if you want numbers, you get 4 plus 12 times 4 minus 1, so that's 4, and you can get the value. If you actually calculate, divide by 2, divide by 2, 2, 4 plus 12, 16, 16 times 2, 32. So our answer is, we're expecting an answer of 32. Again, this is equal to, not similar. We're looking for exact values because we're using the definition with n intervals, not a certain number, so we're not approximating anymore. So this is what it means to look for the area of a trapezoid, or like using the area of trapezoid for this. It's not a modification of the rule, it's just that they're asking you to do two of them, the definition and the area of the trapezoid. I did this first just to show you that we're expecting this. I could have done it in the end to show you the suspense, as in, oh, we can get the same value here. So yeah, you know, as the previous ones, we immediately start with delta x, which is b minus a over n. So 4 minus 0 over n, you get 4 over n. And if you want your intervals, that you start from 0, right? So 0 plus 4 over n, you get 4 over n. And then 4 over n again, plus 4 over n, you get 8 over n. And then add 4 over n again, you get 16, sorry, what 16? 12 over n, and so on. So you're going from, never mind. So pretty much to find ck, because I just thought about the normal one with 4 intervals, 5 intervals, but this one is different. It's n intervals. Otherwise I would have continued, so to show you. But anyways, for ck, it's, you have a 0, so 0 plus, so nothing, over n stays constant. Here we're quadrupling, as you can see. So times 4 times 1 is 4, 4 times 2 is 8, 4 times 3, so we're quadrupling k, so 4k. This is actually how to get this. Let me just write it close to each other. So yeah, it's 4k over n. F, although we have that, we only need f of ck. So now f of ck, just put that up. It's 8k over n plus 4, because 2 times this and then plus 4, pretty much. I'm boxing this and this because that's what we need for the summation. So the limit as x, sorry, not x, n, the number of intervals as it approaches plus infinity, we're getting more and more accurate with an absurd number of intervals. It's super small, so you end up literally kind of like adding every single slice of this with extreme precision. So yeah, that's why you end up with the actual area. So yeah, with that times the summation as k goes from 1 till n of f, or we can start with delta x if you want. Delta x times, I usually start with delta x because I know I'll take it out because it's constant. F of ck, it's just a personal choice of writing delta x first. I'm not going to start with equals immediately. This is my area of, by the way, there's this one thing I forgot to mention. One thing Mr. George said, or he wants to kind of recommend us to do, is when you do the area of a triangle, rectangle first, one rectangle, so area of, even for the previous ones, by the way, it also works. Area of one, I'll show you why it works. Area of one rectangle is f of ck, just that, times delta x. And that's why when you do n rectangles, you actually do summation. That's why, pretty much. So this is nothing odd, and this applies to all the other questions as long as they ask for area and using the summation. This applies to all of them. Area of one rectangle is this, nothing to change. This is ck, f of ck times delta x. And area of n rectangles is the summation of f of ck times delta x, as k goes from this to this. And towards the end we want the limit, so if you want you can add the limit, or you can just start with this, keep on going, you reach a certain point, and then you're going to add the limit and then move on with the simplified version and then just finish it off with a limit. Or you can start with the limit in the beginning. So yeah, any is valid, should be valid. If you want to see the book and how it goes about it, because the book is supposed to be the accurate way of solving, the correct. Of course it can be very rigid, so sometimes it's weird, but follow how they kind of express things or say things, not necessarily how they solve. How they solve might be annoying, no need to follow them. Follow what we are doing, because it's usually easier, like what the teachers taught you and all that. So yeah, if you do the summation, you're gonna end up with summation of k f of ck is 8k plus 4 and here over n times delta x, which is 4 over n. Actually, let me just write this in a much clearer. So 8k over n plus 4 times 4 over n. Let's split the summation. So first of all, 8k over n times 4 over n, that's 4 times 8, that's 32, right? 32k over n squared. So I'm taking the 32 over n squared out, and I said k, so we're left with k, plus this times that, you get 4 times 4, 16n outside over n, outside. Summation, nothing stays, so 1. So k1 till n of 1, summation of 1. And with that, 32 over n squared, the summation for this one will be n into n plus 1 over 2, and yeah, plus 16 over n times n. This is where, if you want, you can introduce the limit, and not x, n, as the number of intervals approach plus infinity, we're more and more accurate. So plus infinity, and the summation, if you want to go step by step, f of ck times delta x from 1 till n is the limit as n approaches plus infinity, and then we keep on going. So 32 over n squared, just to write it, to copy it down so that I can show you what you can do next immediately, thanks to the limit, basically, because without the limit there are things that you might not want to do. And because you have the limit and you have the value for the n, this is when you actually can cancel normally, because you need to know that. never mind actually, but anyways, cancel, so you're left with 16, so your limit of that was actually 16, and then 2 this 16, and then this n makes n squared, and same power, so ratio of coefficients, so this answer 16 to 1, so you get 16, so 16 you get 32. Did we or did we not get the same answer as the trapezoid area? We did, right? So this is why they asked you. They wanted to show you that it works, that you're gonna get the same value if you tried you know, using the trapezoid rule. So yeah, pretty much. Okay, so for this one you need to manipulate the integrals. Each one has its own special things, and you're only given, like, for a function you're only given 2 limits for it, or like 2 integrations, 2 definite integrations. So let's start with part A. Part A is a special case. Well, not exactly so special, but it kind of like a lifesaver when it comes to solving, because it's one of the easiest to solve. Easiest, so save your time from this one. 2 to 2, don't think, it's just same limit, immediately 0. If you want to understand why, I have 3 ways to explain this, if I actually forget, or I mean if I remember the 3 ways, because I just thought about them previously. The first one is, for example, graphically. Say you have a graph like this and you want to find the area. You are doing, like, from 2 to 3, for example, let's say like this, you find the area like that. But if you find the area of a point like 2 to 2, which is the point itself, and you end up with a line, lines in math have 0 width and a length, so the area of a line is pretty much 0. They're one-dimensional you know, figures. So with that, you immediately, that's why your answer is 0. Another way to see this is the fact that when you substitute, you know, as in blah blah blah, and integral, like you got the value of the integral of this somehow, and then you do this from 2 to 2. Either way, you're gonna put 2 minus, and then you're gonna put 2. Same expression, subtracting same expressions gives you 0. You're pretty much done. There was, I promised a third one, but I think they're pretty much the same, I guess, not that much. So yeah, you're basically subtracting the same limit. You're just going from a point to the other. It's just, you're doing, it's like saying 0 work, for example, if you're talking about energy and all those. So you're not really doing anything, just from point to a point, same point, so 0 area. B goes from 2 to 1. I'm gonna take the 2 outside. U of x dx. I don't like how it's 2 to 1, personal preference, so I'm gonna change it to 1 to 2. Makes things easier also when you want to see it visually, for example. So minus 2, open brackets. For this part, I have a graphical or a visual representation. So if you have, let's say, the number line like this, this is 1, this is 2, this is 0. So if you want to cross the path from 1 to 2, so you want to go like this, right? But you don't have 1 to 2, you have 0 to 1, you have 0 to 2. So another way, ignoring this, by the way, ignoring these, ignoring them, another way to see this is to go like this, and then like this. The green is an alternative to the red, because this will cancel with this, you end up with this. And you know, like displacement and all that, you will end up with this initial, same initial in both, and also same final in both. So yeah, pretty much. So for this one, it's integral from 1 to 0, important, so you're going from 1 to 0, and then integral from 0 to 2. So let's write that. So integral from 1 to 0 of, let me change the color, let me pick purple, for example. Integral from 1 to 0 u of x dx plus integral from 0 to 2 u of x dx. Minus 2. By the way, I put the brackets earlier because I knew that I'm going to split it into a plus. And of course, if you want to distribute, you will do that, but keep in mind you have a plus, so minus minus in both, like minus here, minus there. So yeah, integral. Do we have 1 to 0? No, we have 0 to 1. So you flip. These small processes make a difference. So that's why I'm doing everything slowly, very slowly, because swapping limits is nothing important. It's really trivial, but it's nothing to underestimate also when doing like mistakes. So now do we have what we want? So we're going, let's read it like this. We're going from 0 to 1. So 0 to 1, and then add, and then negative of that. So you reverse, and then you add to it from 0 to 2. So you get this. So you get this in the end, and then you subtract. You multiply by minus, and you multiply by 2, because that's what they have. They want. They give you 2 to 1. So 1 to 2, again negative, and 2 times because they have 2. So we reached what we want. Just substitute for this one. Minus 2 into minus from 0 to 1, 2. Plus from 0 to 2, minus 1. So minus 2 minus 1 minus 3 times minus 2, you end up with 6. Pretty much. Now for the last and final one, for this one, C. Let's pick, for example, dark blue. C. For this one, you just from 0 to 2. Thankfully, this time you are looking from 0 to 2, and you have explicitly written here, so you don't have to go through this mess again for at least the U part. For the V, from 0 to 2, thankfully you're given from 0 to 1, and from 1 to 2. Just add the 2, you end up from 0 to 2. So not like this, where you have to reform. There might be an easier way, by the way. I'm just showing you how you can go step by step, making 0 mistakes. So yeah, so integral from 0 to 2. I'm splitting it already, if you don't mind. So 2 over 3 into from 0 to 2 to of ux dx plus 1 over 2 integral from 0 to 2 v of x dx. So this is 2 over 3 from 0 to 2. We already have this to be minus 1. So minus 1 plus half of. If you want to see the slow steps, fine, I don't mind. So from 0 to 2, it's from 0 to 1 and 1 to 2. So 0 to 1 of vx dx plus from 1 to 2 vx dx. And we are nearing the end. If you want to save time or space, actually, this 0 to 1 is exactly the same over there. So this is actually, if you want, let me write, no need. So yeah, minus times this, so minus 2 over 3 plus half into, this is where you simplify. So from 0 to 2, 0 to 1, 0 to 1, 2 over 3 plus 1 to 2 minus 2. So here it's actually minus 2, because plus minus, I don't want to write the plus, so minus 2. If you do the calculation, you get 2 over 3 minus 2, you get minus 4 over 3 times half, and plus, or actually minus, because you have a minus, 2 over 3. You get minus 4 minus 4 over 3. Final answer for the limit. And you're pretty much done for this question.
You guys, so this is 5.3. So we'll start off with the section beginning. So the average value of f of x. So for average value, what you need to do is, what it basically means is the area divided by the width. So for example, you have these few points, you have these few graphs over here. The first one is just a straight line. So the average value will obviously be the value over here, the y value over here. Let's say it's a. For this straight line over here, where it's not horizontal and it slopes up, the average value, will be at a midpoint over here, Why? Because it's basically going up in the same, like every 2 or sloping up every 3 units, and you have uh, a straight line and you just take the average of it, so it's pretty simple. And then for the next one, where you have a graph of, let's say, I think it's like x squared plus 2 or x squared plus 3, you can see that it spends most of its time over here in the bottom. So instead of being at the middle, it'll be somewhere over here. The y value will be corresponding with somewhere over here, which might be a little over the actual starting point, because it spends a lot of its width down here. So even with this high value at the end, it will contribute, but it will, because it wasn't like a straight line here, it will actually lower this, because it spends most of its time at a lower y value. So the next one, so we'll take a few examples. Here, x squared plus 5. So the formula for the average value is integral from a to b of f of x. And that basically means you find the area under the graph over here. Then you divide by the width. So b minus a. So this is a, and this is b. So b minus a is the width. So then you'd find the average y value in terms of the area, you know. So if we were to do this mathematically, integral of 0 to 3 x squared plus 5. So you can just enter that on your calculator, or you can solve it, you know, mentally. So it'll be x cubed over 3 plus 5x, and then this function from 0 and 3. So the answer becomes equivalent to 9 plus 15, which is 24. So 24, that's the area. So to find f average, you divide the area by the width. So it will be 24 divided by 3 minus 0, which is equal to 8. And that is the average value. Next one. So this is the next point of section 5.3, the mean value theorem. For a definite integral extending from a to b or any point, there always exists one value, x equals c, such that f average equals f of c. And obviously this is for continuous functions, because if it wasn't continuous, then there might have been a gap. Like let's say instead of this point, it just goes up here, and then but down here with a gap. So obviously you wouldn't have that value, so you couldn't say it. So it has to be continuous. So you do it as regular, you find the f average like last time, integral divide by width, and then f of c. That is where the additional point comes in. You have the function inside the integral, and you simply equate it to f average, and you can find out what c is. And to get the y value of c, you simply substitute it in, and you'll get it, which is the f average, by the way. So here we have an example. F of x of equal to 3x squared plus 2. Find f average. So integral, do it in different color. Integral. They have to give a parameter, like an interval. So let's say from 0 to 3, like last time. Integral of 0 to 3 of 3x squared plus 2x dx. Then you just solve a normal integral. 3x squared is x cubed over 3 times 3, so it just becomes x cubed, and then plus 2x, plus 2, and then becomes plus 2x, and then from 0 to 3. So this is equivalent to 3 cubed, which is 27, plus 2 times 3, which is 6. So 27 plus 6 is 33. And then minus 0 cubed plus 2 times 0, so 0. So it is 33. Now that is the area. F average is equal to the area over the width. So b minus a 3 minus 0, which is equal to 11. Now you need to find the x value, which is c, such that the f average that we got, which is 11, is equal to f of x, or f of c. So if you simply equate it, 3x squared, or actually let me put that as c, 3c squared, because this is f of c, f of c equals 3c squared plus 2, which is equal to f average equal 11. So 3c squared plus 2 equal 11, and then you end up with c equaling plus or minus 11 minus 2, which is 9, and then you divide it by 3, because 3, you get 3, so plus or minus root 3. But notice that they said that c is a value in between the interval, so between 0 and 3. So it's not negative, and it's simply plus root 3, and that is the value of c. Okay, so continuing with 5.3, first fundamental theorem of calculus. So this basically implies, or this states, that for the integral of f of t, where you have a parameter from a to u can be anything from, it can be like x, or it can be x squared, but I used u instead of x, so you know what to do when you have something that whose derivative is not 1. So it states that for the integral of f of t dt, it's equal to the derivative of that is equal to the function but of u. But remember, this a is a constant, it has to be a constant, and then its derivative is equal to function times the derivative of u. So let's say you have this function, and then d of this is 2t plus 3, but this is a constant, so you're good, and then x power 4. So you just sub in x power 4, so 2x4, as in this was t before, and then 2x power 4 plus 3 as regular, and then you multiply by the derivative. It has sort of a similar appearance of chain rule. If you consider this to be the exponent, then you have this as a derivative. It's not mathematically similar, but you can memorize it, or you can understand it, or have the ease of memorizing it that way. Now let's do an example. So here we have a function, and then we are asked to find the derivative of an integral. So it is a function itself, but what do we substitute for t? Obviously, from the first fundamental theorem of calculus, you have to have a in the bottom, the constant in the bottom, but this is u, and that is a 4. So you put a minus for the answer, because you need to flip it. So then it becomes minus integral of 4, and then x cubed, and then root 1 plus s sine t in dt. Okay, so now you put it in the proper way, it's a minus, and then all you have to do, according to the first fundamental theorem of calculus, is just plug x cubed in, and the constant doesn't matter. So it becomes root 1 plus sine, and then t is, you just put in the x cubed, this value, x cubed, and then you multiply by the derivative of x cubed, which is 3x squared. That's the answer for that. So minus root 1 plus sine x cubed, and then outside the root 3x squared. Next one, the secant from x to x squared. Here you have to apply the first fundamental theorem of calculus, but you have an integral that is not a constant, so you basically have to separate it into a constant. So you equate this into integral of x and x to 0 and then secant t dt plus, actually not 0, make it any constant a such that it's between x and x squared. You'll see that it cancels out, so it doesn't really matter whatever you put in there. And then this becomes x squared plus, by the way, plus x squared and a as well, and then secant dt. Basically, you're just separating it. Here you have x squared, so you're fine, but here you're not fine because you need the constant to be the lower bound of your integral. So you put a minus. So it becomes minus, because you want to flip the x up, you want to put the upper bound, minus secant x, and then plus secant, and then you plug in the upper bound because it's a constant, the lower bound is a constant, minus plus secant x squared. So if you want, you can simplify this and you will get the same answer, and it will probably be one of the choices for multiple, or written in this case because the periodic is written. Next one, the second fundamental theorem of calculus. This is basically very simple. It's what we did. So it basically defines what a definite integral is. So if you have a function f of x, which is the integral of the small function f of x without any bounds, so you're going to have plus c, then integral of the definite integral with bounds a and b of f of x is equal to the capital F of b minus capital F of a. So this is basically defining the definite integral, and it's what we've been doing the whole time. Or you just enter it into a calculator, you'll get the same result. So this is basically the definition of a definite integral, and what you do with the lower and upper bounds. So it's pretty much that's it. Nothing too hard. So let's move on. So we'll just do regular integral. So this is a pretty hard one if you're not given the clue that is here. If you're not given the clue. So sine squared x, normally for, let's say, a variable squared, you would just put it, make it add 1, then divide by it. So like x squared becomes x cubed over 3. But this is sine. You have to divide by the derivative, which is cosine. And then once you do that, you'll end up with x again, and it won't really work out. So what do? You need to figure out a way to get rid of the squared. And then we know, or it won't come to your memory because this is a bit complex, or it's not complex, but it won't just come to your memory or come to anyone's memory unless you have been properly immersed in the subject. So cosine 2x equals cosine squared x minus sine squared x. It's identity. That's how you solve this question. And then cosine squared minus sine squared. Cosine squared is 1 minus sine squared, and then you add minus sine squared again. So it becomes 1 minus 2 sine squared. Then sine squared, once you just shuffle things around, so cosine 2x equals minus 1. Cosine 2x minus 1 equals minus 2 sine x squared x. You divide by minus 2, and then you get this formula. So once you do, you just substitute so it becomes integral b and a. I won't repeat it. Of 1 over 2 minus cosine 2x over 2, then dx. Here now you just do a simple derivative, integral. So half becomes half x, and then minus cosine 2x becomes, since it's cosine and you're doing integral, so minus cosine, integral is minus sine, so it becomes minus sine 2x, and then you divide by the coefficient of a, so over 2, and then you have this 2 as well, so times 2, from pi over 2 to pi over 4. You just plug it into the calculator and you get the answer. Obviously pi over 2 you plug in, and then minus whatever you plug in with pi over 4, whatever the answer you get, and you get the answer. Next one, cosecant squared. Here you might not know what to do immediately, obviously you have to think back to a previous identity. So for cotangent it's equal to cotangent of ax is the derivative, so y prime is equal to cosecant squared minus a cosecant squared. I'll make it better. If y equals cotangent ax, then y prime equals minus a cosecant squared ax. And you don't have to worry about a now because it's x, it doesn't have any coefficient. But if you did, then you would simply divide by it. So minus cosecant squared is the derivative of cotangent is minus cosecant squared. So therefore, the antiderivative, the opposite derivative of cosecant squared is minus cotangent. Always the minus, it just flips between them. If you have a positive, the other becomes minus. So then the integral becomes minus cotangent bounded by minus cotangent x bounded by pi over 4 and pi over 6. So then you take your calculator out, you do minus 1 over tangent x, sorry not x, pi over 4 minus 1 over tangent pi over 6. Remember to keep it in radians, the calculator in radians. So this is pi over 4, it's minus 1 over 1, and then tangent pi over 6, it's 30 degrees, so sine is half, and then cosine is root 3 over 2, so it becomes 1 over root 3. So minus 1 over root 3, so this becomes positive, and root 3. So the answer is root 3 minus 1 for this whole question. Next up, we have substitution. This is pretty easy. It's what we did again. We're just restating it. So if you have a function and you want to simplify it, you can just take a equation that's really messing with the integral and just make it u, and then divide by the derivative of that u, which is u prime. And then this is how you convert dx to du. And obviously u is in terms of x, so that's why you can't just take it out, otherwise it would be a constant. Obviously just divide by derivative. So an example, cosine x cubed sine x. So in these exams they'll give you sine x, or they won't give you sine, but they'll have sine x in the function. So when you divide by the derivative, it'll be very simple for you. So it will cancel out perfectly in that. So u equals cosine x, du of dx equals to minus sine x, the derivative. So if you can't mathematically do this, but you can do it for visualization. So du then becomes minus sine x dx. So here you have sine x dx. So you can't, you can just take it away, but you need the minus. So then it becomes integral of minus u cubed du, and then the bounds you put cosine, it's u, so you just substitute these in. So cosine pi over 3, it will be cosine 60, so half. Then cosine 0, it will be 1. So this then becomes minus u power 4 over 4 of half and 1. And then you put it in the calculator, and you should get a value, it will be a fraction, and it will be of order 16, or yeah, it will be of order 16. So something over 16. And that's it for this question. Now, last question before we move on to the grid that Ali Tabaza will do. Over here. This is what's causing the problem. You can't just put the x in, or you can't just get rid of the... You can put the x in if you make it x squared, but then you still have a problem with the radical. So let u equals x squared plus 4. Let du over dx, let's say, I'm putting it dotted so you can see it later. That doesn't visualize it, so I'll just move it. And then derivative 2x dx. Here you have x dx, so you need a 2, so the 2 becomes a half. Why is it in the denominator? Because you divide by the derivative, or you need a derivative. So let's say it's you multiply by 1, so it'll become 2 over 2. And then the 2x will go for u, 2x, the 2 will go up, and then a half remains. So at the end, you're left with integral of half, let's just move it outside, root u du. And then you change the bounds. So x squared plus 4. So 3 squared plus 4 is 9 plus 4, 13. And 0 plus 4 is 4. Now, integral of root u. U is just a variable like x now. You don't have to treat it differently. That's because you changed the bounds. Otherwise, you'd have to put the x squared plus 4 back in if you didn't change the bounds, but you did. So, root u is u power half. Now, integral, you just add 1, so half plus 1 is 3 over 2, and then you divide by the new power you got, so 3 over 2, so it becomes multiplied by 2 over 3. So, 2 over 3 into u power 3 over 2. That's a wonky 3 over 2. And then the bounds, 13 over 4. And don't forget the half from outside. So these cancel. So it just becomes 1 over 3. So now, 1 over 3 of root 13 cubed minus 1 over 3 of root 4 cubed. Put that in the calculator, you'll get it. Or if they ask for a simplified version, you just expand it. Expand the 13 cubed, check for any factors. There's a function on the calculator, I think it's in ENG or F fact. It's like factorial. Sorry, not ENG. Factorial. Once you press it, then it will give you factors. And then 4 cubed, it's pretty simple. You just take multiply, or you don't multiply, it's 2 times 2, so 2 goes out, so 2 goes out 3 times, so it becomes 8, so minus 8 over 3, and that's it.
Let's move on to the grid, and grid questions number 29 and 30 are relevant to this section, and I'll give you guys a few seconds and we'll solve them together. Okay, let's solve it together. A function is defined implicitly by the equation 2x cubed plus 2x plus y squared minus 3y equals 2. In the xy plane, the slope of the tangent to the graph of the function at the point 1, 1 is equal to k, where k is a constant. Find k basically. So all you have to do is find the slope. So find the derivative and substitute 1, 1. So that's very simple. 6x squared plus 2 plus 2y y prime minus 3y prime is equal to 0. Take the y prime out. 2y minus 3 is equal to minus 6x squared minus 2. So y prime is equal to minus 6x squared minus 2 over 2y plus 3. Sorry, 2y minus 3. Now they want at 1, 1. So we do it at 1, 1. And we get minus 8 over 2 minus 3 is minus 1. Cancels. The answer is 8. That's the slope, and that's what they wanted. So 29 is very simple. 30 is a little more challenging, so we'll do 30 now. 30 we are given that y squared minus x squared is minus 64. We need y prime at y minus 2. Okay, so y squared minus x squared is minus 64. We need y prime, so y prime equals question mark when y is equal to minus 2. So first we need to find y prime, so it's y prime is equal to, let's see, 2y y prime minus 2x. Let's not call it y prime to make it simple, f prime of x, if it'll look better, is equal to 0, right? So y prime is equal to 2x over 2y. So here's the y prime. Now to find y double prime, we do quotient rule. So it's 4y minus 4x y prime, over 4y squared. You square the bottom, it's 4y minus 4x. You substitute, you get 2x minus 2y, all of that over 4y squared. I'm gonna continue here, 4y minus 8x squared over 2y, over to give 4y squared. You have to do common denominator, it's 8y squared over 2y minus 8x squared over 2y over 4y squared, right? 4y squared. You take the 2y to y down, it's 8y squared minus 8x squared over, let's see, 8y cubed. Cancels. We know that y squared minus x squared is minus 64 over y cubed, which is minus 2 cubed. So it's minus 64 over minus 8 is equal to 8. And that's our answer. So these are two questions related. 32 is a direct application. 31 is coming in the exam. It's covered last year. So let's do them both. I'll give you guys a few seconds. You guys can solve 31 and 32 and then we'll check together. Let's do 31 now. The volume of a sphere is increasing at the constant rate of 5 cm cube per second. When the radius is 5 centimeters, it increases at a rate of 1 over k pi centimeter per second, where k is a constant. Find k and enter its value as a whole number. So in this question, basically it's dv over dr, dv over dt is equal to dv over dr times dr over dt. It's equivalent because this cancels. Let me just fix this. dv over dr times dr over dt, right? We have dv over dt. We have the rate of change of the volume. It's constant, dv over dr. We're looking for this. So this is in effect dr over dt is equal to dv over dt by dv over dr divided by the rate of change of the volume is 5, and this is the derivative of the volume, which is 4 pi r squared when r is equal to 5. Moving on here, or let me just continue here. We get 5 over 4 pi 5 squared. This cancels, 1 over 20 pi. So k is 20. I'll give you guys a few seconds to check and then we'll do 32. Okay, let's check 32 now. Consider the function f given by y equals f of x equals x cubed minus 3x squared plus 2x, and let L of x be the linearization of f at x equals 0. What is the value of L of 10? Okay. Let's check f prime of x. You immediately find the derivative. It's 3x squared minus 6x plus 2. And this is at x equals 0. So this is all gone. It's 2. Just fix that. Yeah. Now we get y minus 0 because it was 0 in the beginning into 2 into x minus 0. So it gets y equals 2x, which leads to L of x equals 2x. They're asking us for L of 10. So that's 2 times 10, giving us 20. And this is the answer. Grid application. Let's do grid question number 33. I'll give you guys a few seconds to solve. Okay, let's solve it. Consider the function f given by y equals f of x equals this. Let x0 equals 1 be an initial estimate for the root of f of x equals 0. The next estimate for a root of f of x equals 0 using Newton's method, this is important, is x1 equals minus k over 3, where k is a whole number to be determined. Give the value of k. Newton's method is something we did not cover. I feel like they meant for it to be self-studied, but since it is part of the grid question material, let's just have a quick go over it. And since they only want the next estimate, it's a very short and easy question to do. So let's solve. So what Newton's method wants us to do is, basically it's xn plus 1. So the next estimate is x0 minus f of x0 over f prime of x0. That is the formula. We have x0, we can get f of x0. We don't have f prime. So let's just quickly find f prime of x, which is 6x squared minus 3. 6x squared minus 3, right? Now let's see. x0 equals 1 is the initial estimate. So x of n plus 1, or let's call this x1, equals 1 minus f of 1 is, let's see, 2 minus 3 is minus 1, 5 over. Now 6 squared, sorry about that, 6 times 1 minus 3 is 3. So basically it is 1 minus 5 over 3. Substituting, you get 3 over 3 minus 5 over 3 minus 2 over 3. So k is 2. And that's how you solve grid question number 33.
Okay, question 43. For f of x equals x squared minus 2, find c for average value, and then find c squared because most likely it will be in a radical form. So average value, you find it by dividing the area under graph by the width. So you're finding the average height, if you can get the intuition of that. So the formula is integral of x squared minus 2 dx over, from 0 to 2, obviously, 2 minus 0. Now, over 2 of x cubed over 3 minus 2x dx, not dx, sorry, it's this form where it's from 2 to 0. So then the final answer will be, for average, f average, x cubed you sub it in, so 2 cubed, 8 over 3 minus 4, so 4 is 8 over 3 minus 4 is 12 over 3, so 8 minus 12 is minus 4, so it's minus 4 over 3, and then divided by 2, it's minus 2 over 3. That's the average value. So minus 2 over 3 is equal to x squared minus 2. Or actually, let's make things simple. You substitute in c, so it ends up being c squared minus 2. And then move 2 to the other side, so c squared becomes 2 minus 2 over 3, which is equal to 6 over 3 minus 2 over 3, so you end up getting 4 over 3. So if you notice, we already got this form. C squared equals something over 3. So k over 3 equals 4 over 3, so k is 4. C squared equals 4 over 3 equals to k over 3. So the answer is 4. And that's it for 43.
So in question 44, they ask us to find the integral going from 3 to 0 of 3x squared radical x cubed plus 9 dx. So for this question, we have to use the substitution method. So we say that u is equal to x cubed plus 9 So then we derive it and it becomes du over dx is equal to 3x squared. Then what we have to do in the substitution method is make dx the subject of the equation. So dx is equal to du over 3x squared. So then the integral becomes 3x squared radical x cubed plus 9, which is equal to radical u. And then we substitute du over 3x squared in the place of dx. So then the 3x squared and the 3x squared cancel out, so the integral becomes radical u. And then if we integrate that, it becomes x cubed plus 9 to the power of half plus 1 over half plus 1, which is equal to 3 over 2. In a simplified version, this becomes 2 over 3 times x cubed plus 9 to the power of 3 over 2, going from 3 to 0. Then when we simplify it, it becomes 144 minus 18, which is equal to 126. Question 45 asks us to find the integral from pi over 10 to 0 of sine 5x cosine squared 5x dx. This question we also have to use the substitution method. So we say that u is equal to cosine 5x. So the derivative, or du over dx, is equal to minus 5 sine 5x. We make dx the subject of the equation, so dx is equal to du over minus 5 sine 5x. So the integral from pi over 10 to 0 becomes sine 5x cosine squared 5x times du over minus 5 sine x. And then we can cancel sine 5x with sine 5x, and it becomes minus 1 over 5 integral u squared du. And then we can integrate u, so it becomes minus 1 over 5 times cosine cubed 5x over 3, going from pi over 10 to 0. If we simplify, we get 0 minus 1 over 15, which is equal to 1 over 15. So then in this question, k is equal to 15. Question 46 asks us to find the integral from x cubed to x of 5 theta cosine pi theta d theta. But as we took, the integral can't go from a variable to another variable. It has to go from a constant to another variable. But we can use the principles we took to do that. So we can write the integral going from any constant, I chose 0, to x, 5 theta cosine pi theta d theta, plus going from x cubed to that same constant of 5 theta cosine pi theta d theta. We can switch the first integral so that it goes from x to 0, but in order to do that we have to add the negative sign before it. Now the question wants us to find f prime of minus 1, so then it becomes minus 5x cosine pi x plus 5x cubed plus 3x squared times cosine pi x cubed. Now if we substitute minus 1 into that equation, we get minus 5 plus 15, which is equal to 10. Question 47 asks us to find the integral from 5x to x of 15 cosine squared w dw. Again, we have to split the integral so that they go to a constant. So they go from 0 to x, 15 cosine squared w dw, plus 5x goes to 0, integral of 15 cosine squared w dw. And we flip the first integral so it becomes minus from x to 0, 15 cosine squared w dw. They want us to find f prime of 1, so it becomes minus 15 cosine squared x plus 15 times 5 cosine squared of 5x. And if we substitute 1 into that, we get minus 15 plus 75, which is equal to 60.